In a previous lecture, we talked about the second law of thermodynamics, and in this part of the lecture, we're going to talk about calculations that you can do using the second law of thermodynamics. All right, there are four general types of calculations you can do depending upon the conditions. For an isothermal change, we'll go back to these in just a minute, but isothermal, for non-isothermal processes, and then for isothermal volume changes, ideal gas, PV work, we have this, and the pressure changes, we have that. All right, so those are the four basic equations we're going to use to do some calculations with the second law of thermodynamics. Now, let's talk in more detail about this. This is isothermal change. Let's start from our definition of entropy. ds is dq reversible for a reversible process divided by temperature. All right, let's integrate both sides. Let's integrate ds. S is the state function. This will be just delta S, the difference between the final and initial entropy changes, entropy. And this then will be the integral of dq reversible over T. So far, so good. And now let's make the assumption we have constant temperature, so we can pull that out. And this will just be integral of dq reversible. And our assumption here is constant temperature. And we'll just call this integral of dq reversible the total heat transferred in a reversible process in going from the initial to final state. This is just q reversible over T. So if we have a reversible process, we just look how much heat we've transferred, divide by the temperature at that constant temperature, and that's the entropy change in going from your initial to final state. That's that one. Now, what happens if the temperature is not constant? Let's take a look at this. All right, again, we'll start with our definition of entropy. Entropy is dq reversible over T. And we'll integrate both sides, going from initial to final state, ds. This will be just delta S. This will be integral of dq reversible over T. Now, temperature is not constant, so we can't pull this out of the integral. However, we do know that for a reversible process, or in general for anything, d reversible is the heat capacity times the change in temperature. Or since we're doing infinitesimal changes here, let me write this as dt. All right, so if that's the case, we can put that up there, change the variable of integration. So this now will be the integral of 1 over T times the heat capacity times dt. And let's make the assumption that heat capacity is a constant. We can pull this out of the integral. So the heat capacity, the integral of 1 over temperature dt, constant heat capacity C, and the integral of 1 over T is just C times the natural log of the final temperature divided by the initial temperature. This is how you would calculate entropy changes if the temperature is changing. Okay, let's go here. Let's see, put some more restrictions on. Isothermal volume, ideal gas, only PV work. Yeah, let's start again. Once again, from ds is dq reversible, heat transfer in a reversible process divided by T. Integrate both sides, integrate ds. This will just be delta S, initial minus final minus initial. It's the integral of dq reversible over T. And now let's make it isothermal, constant T, 1 over T, the integral of dq reversible. We're integrating over that. Now we're going to make the assumption isothermal and only PV work. So isothermal, remember that du is equal to 0 for an isothermal process for an ideal gas. That's one of our restrictions here. This is dq, and let's make this reversible, plus dw reversible. So this is an ideal gas, and that is equal to dq reversible minus PdV, the assumption here is only PV work. So in other words, dq reversible is just P dV. Okay, so let's go ahead and do that. Hello, there we go. So now we have delta S is the integral of dq reversible, which you just said was P dV, and we said temperature was constant, 1 over T, P dV. Here's pressure, here's volume. We need a relationship to integrate this, how pressure depends on volume. And by the way, we made the assumption of an ideal gas. Constant temperature and only PV work. That's how we got to this equation. 1 over T, the integral. Since it's an ideal gas, we know how pressure depends on volume. Pressure is just equal to nRT over V dV. Oh, that's nice. We're going to make an assumption of constant number of moles. We're not adding or subtracting anything into it. This would be 1 over T. We're pulling N and R and T. It's constant T. We can pull that out. So this would just be nRT, the integral of 1 over V dV. Note how the T's cancel out. So this is just equal to nR. Integral of 1 over V is just natural log final volume over initial volume. All right, so that's where we get that equation. And then if we make the same kinds of assumptions, we can just immediately change this into a pressure change. Because we know for an ideal gas at constant temperature, V2 over V1 is equal to, just erase this. Let's see if I can control E. That's the eraser. Okay. So that's equal to P1 over P2 for an ideal gas. This is Boyle's law, essentially. So we can say that delta S is equal to nR times the natural log of, we're going to substitute in for V2 over V1, P1 over P2, and that's equal to minus nR times the natural log of the final pressure divided by the initial pressure. Okay, so that's that one. So those are where those four equations come from. We all start with the definition of entropy. ds is equal to dq reversible divided by temperature. Let's use these equations to do a few examples. Here we have 0.5 mole of steam at 100 degrees. Little mistake here. Is condensed to form a liquid and then cooled to 0 degrees C, then frozen at 0 degrees C. And just let me say at 100 degrees C. So this is an isothermal condensation of steam into liquid water. Then when you have that liquid water, you're going to cool it down to 0 C. So you have liquid water at 0 C, and then you're going to freeze that water at 0 C. Let's calculate the total entropy change for these processes. And here's some useful information here. We have the enthalpy of fusion, we have the enthalpy of vaporization, we have the heat capacity of liquid, and everything is done under constant pressure. All right, so let's calculate the entropy changes for these. Pictures sometimes useful. So we're going to start with steam at 100 degrees C, and we're going to condense that into a liquid at 100 degrees C, and then we're going to cool that liquid down. We still have a liquid at 0 degrees C, and finally we're going to change that liquid into a solid at 0 degrees C. Now it looks like this is a phase change, and we'll calculate delta S for that. And this also is a phase change. And here, we're just cooling a liquid. All right, so phase changes occur at constant temperature. The way we've written it here, 100, 100, temperature doesn't change. The phase change, the Q that you transfer from a frozen to a liquid, or a liquid to a frozen set of molecules, that is actually a reversible process. Doesn't do any work, but that's a reversible process. So this is reversible. And we can think of a reversible process, well, we just cool this down. This is also reversible. So let's calculate each step, delta S1, delta S2, and delta S3. And since entropy is a state function, the total entropy change will just be that, plus that, plus that. All right, so let's select delta S1. That, because it's a reversible phase change at constant temperature, we can go back up here, isothermal change, and we have a reversible process, so the heat transferred in or out of the system is for a reversible process. This is how you calculate delta S. So the first step is Q reversible over T. Okay, Q reversible, let's see, we have steam and we're going to make it into a liquid. What's the sign of Q for this process? Well, it should be negative. I mean, if you go this way, you have to put in heat to boil, go from a liquid to a vapor. Going the other way, you release heat. Okay, so that's why steam actually burns, even though the temperature doesn't change. It's because as you go from steam to a liquid, you're releasing heat, and that heat goes into your skin, and you say, ow. All right, so what's the reversible heat transferred there? Well, let's see. What we have in the problem is the specific enthalpy of vaporization of water. So that's how much heat it takes to 2.257 kilogram per joule. That's how much heat we would have to take 1 gram of water and change it from a liquid to a vapor. We're going the other way around. So we're going from the vapor to the liquid, so this would be a negative sign here. All right, so if we have a gram, this would be 2.257. I'll put times 10 to the third because we want, the problem specifies we want in joule per Kelvin. All right, so this is joule per gram of water. That's an intrinsic variable. We want to change that to the extrinsic heat capacity, so we have to multiply by the amount of water here. We're given 1/2 mole of steam. We have to put in a gram, so that could be easy, 0.5 mole. And then, let me just continue this down here. We have 18.01 gram per mole. So there we have the how much heat you actually transferred for 1/2 mole, or that's how much heat was released when you went from the steam to the liquid. We're going to divide all of this by the temperature. The temperature is 100, but remember this temperature is in Kelvin, so we'll have to change to Kelvin to 73.15. And this comes out to be, plug those numbers in, minus, don't forget that minus sign, 54.50 joule per Kelvin. All right, so that's what it is for the first step. And note the entropy decreased. Sort of makes sense. You have steam, gas molecules, and now you're going to a liquid. So yeah, the entropy would decrease because a liquid, qualitatively, you would think a liquid would have less entropy than the steam. So the final minus initial will be negative. Now let's look at this second step here. We're taking a liquid and cooling it down to a liquid. No phase change occurring here. So what is happening? Well, we're changing the temperature. 9 isothermal changes. We're changing the temperature. We know what the heat capacity is. We can figure what the entropy change is for that second step. So let's actually do that. So delta S for the second step, just changing temperature, heat capacity times the natural log of the final temperature divided by the initial temperature. The heat capacity given in the problem, the specific heat capacity is 4.184 of liquid water, joule per gram Kelvin. This is 4.184 joule per gram Kelvin. This is the intrinsic heat. This is an intrinsic heat capacity. This is an extrinsic. We have to actually know what the heat capacity is of our system. So we said we have 0.5 mole, and we have 18.02 gram per mole. So this will give you how many grams you have. That will give you the real heat capacity. Sorry, I'm running out of room here. Times the natural log of the final temperature. Final temperature, 0. Let's go up here. Final temperature was 0. Initial temperature was 100. Okay, so final temperature, again in Kelvin, don't forget Kelvin, 273.15. The initial temperature was 373.15. Put these numbers into a calculator and you get minus 11.77 joule per Kelvin. Again, it's negative. So we expect it negative. Yeah, you have things moving around here at 100 degrees, and now you're moving at 0 degrees. So qualitatively, you expect that entropy will be negative. Or if you look at it the other way, in order to heat up the liquid, you got to put in heat to the system, increasing entropy. Going the other way, cooling it down, you got to take heat out. The system is losing energy, is losing entropy, so entropy should be negative. This is for the second step. Now let's look at the third step. The third step is a phase change, just like we did here. Only we're going here, and we're taking heat out, so it should be negative. And we're given in the problem for that phase transition, yes, here it is, a molar enthalpy of fusion. Fusing is melting, and we're solidifying, so we'll have a negative number here. So for that third step, delta S3, that's equal to just Q reversible, which we can get from a phase transition divided by the temperature of the phase transition. And here I'll leave more room here. So in the problem 6.01, we have to figure out how much heat was put in, so we know what the molar enthalpy of fusion is. 6.01 times 10 to the third joule per gram per mole. Sorry, let me go back here. Kilojoule per mole. Enthalpy of vaporization. Oh, I seem to be hallucinating here. So 10 to the third joule per mole. Duh. Okay, joule per mole. We have 0.5 mole. So this will give us how much heat in joule that it takes, or that actually is taken out of the system to take a half a mole of water in a liquid state and put it into the solid state at 0 Celsius. And again, T is in Kelvin, 273.15 Kelvin. So the entropy change here, putting those numbers in, minus 11.69 joule per Kelvin. So the total entropy change, delta S, is delta S1 plus delta S2 plus delta S3. And that's equal to, let's see, what are our numbers here, minus 54.5, minus 11.77, minus 11.69. Adding all those up, we get minus 77.96 joule per Kelvin. All right, so that's how one does those kinds of calculations. Let's do another example. We have an ideal gas, has a heat capacity of 20.78 joule per mole Kelvin. Again, this is the intrinsic heat capacity. To get the heat capacity of a problem, we need to figure out how many moles we have. All right, so this ideal gas occupies 11.2 liter, 1 atmosphere pressure, 0 C. The volume of the gas is increased to 22.4, and the pressure is decreased to half an atmosphere, all at 0 Celsius. So the temperature remains the same, and you're doubling the volume and decreasing the pressure, as you might expect for an ideal gas. Calculate the entropy change for this process. Okay, so, well, maybe we'll go back here and see what sort of Oh look, isothermal volume changes. So it was isothermal. The temperature didn't change. The volume changed. It was an ideal gas. We're doing only PV work, so it looks like that would be a useful equation to use. So we'll use that one. Delta S is equal to NR times the natural log of the final volume over the initial volume. How many moles do we have? Well, you can say N is equal to PV over RT, but you can also remember at 1 atmosphere and 0 degrees C, ideal gas, volume is equal to 22.4 liters. Okay, go back up here. Sorry. We have 11.2 liters at 1 atmosphere, 0 C. If we had 1 mole, it'd be 22.4. So this implies that N is a half a mole. Or you can go ahead and plug it in here. Well, either way, you get it 0.5 mole. R is 8.314 joule per mole Kelvin. You can also use, as you do in here, 0.08 to 1 liter atmosphere per mole Kelvin. We prefer it in joule because the problem asks, oh, it doesn't ask, so let me put in here, in joule per Kelvin. So let's use the R that has a joule in it. And I did poor planning on my screen real estate here. So let's see what I can do. Okay, so this is a separate. So now we have to multiply this by the natural log of the final volume, 22.4, over the initial volume, 11.2. So the entropy change for this process comes out to be 2.88 joule per Kelvin. All right, note that's positive. Sort of makes sense if you have a gas at 1 volume and then you increase the volume. Yeah, entropy would probably increase, and it does with positive value. Now you're probably, or maybe you're not probably, but maybe you are wondering, well, what about the pressure change? So I changed the volume, so what about the pressure? I mean, don't you have to take that into account? Well, it's either one or the other. We'll just go ahead and use the pressure change. Delta S is minus NR times the natural log of the final pressure over the initial pressure. So it's minus 0.5 mole, 8.314 joule per mole Kelvin, times the natural log of the final pressure, 0.5, initial pressure, 1, and this comes out to be exactly the same, 2.88 joule per Kelvin. So you either do it one way or the other. Because it's an ideal gas, you have PV is equal to nRT at constant temperature. This is a constant. So that means there has to be a relationship between pressure and volume. You can't change. You can change one, but then the other has to be calculated from this equation, the ideal gas equation of state. So you don't really get 2 degrees of freedom. There's no really two contributions to the entropy change. You either did one or the other. They're one and the same. So that's the entropy change there. Okay, and then finally, this is not a numerical problem, but just think about it. Consider a refrigerator, bad assumption, but let's do it anyway, as a Carnot engine running in reverse. And why do refrigerators run more in hot weather? All right, so let's write down the Carnot engine. Remember, we had a high temperature reservoir. We had an engine. And then we had a low temperature reservoir. Heat was transferred from the high temperature reservoir to the engine. The engine then did some work on the surroundings, and then some heat was transferred to the low temperature reservoir. Okay, so that's a Carnot engine. Now let's run this in reverse. Let's do work on the system. So somehow we have some external thing here. We're going to we'll do work on the system as refrigerator. So what we're going to do is separate the two, so actually drive a temperature gradient by doing work on the system. So this is now our refrigerator. And again, we'll have the low temperature reservoir. And this will be the inside of the refrigerator. We want to cool down. Here we have the high temperature reservoir. And this will be, I don't know if you ever looked at the back of a refrigerator, there's some coils back there, and that's the high temperature. And what we want to do is do work on the surroundings. So in this case, heat is transferred from the high temperature to the engine. The engine does work, and there's some heat transferred then from the engine to the low temperature to do that cycle. In this case, what we're doing is we want to take heat from the low temperature reservoir, cool the thing down, and put it in the high temperature reservoir. So that's a refrigerator, which is a heat engine running in reverse. Now remember, for the efficiency of a Carnot engine, we have efficiency as 1 minus the temperature of the low reservoir divided by the temperature of the high reservoir. So if we have a very efficient engine, we get a lot of work out for the amount of heat we're transferring here into here. Now we want to transfer some heat here. So it's sort of the opposite here. So in this case, you're having the heat flow from the high temperature to the low temperature. Here you want to go reverse. So you would think, oh, how much work do I have to do if this high temperature reservoir is sitting in a hot room, for example, in the refrigerator, those coils in a hot room? That means that you have to transfer a lot more, do a lot more work in order to transfer that heat from here to here. If this is already, this is, say, the room. So here you have some heat, and now the heat's going to be transferred from the coils in the back of the refrigerator into the room. If this room is high temperature, you're not going to have very efficient thermal. So you got to do a lot of work to pump that heat out of the low temperature into the high temperature reservoir. And if it's in a hot room, you got to do more work. All right, so qualitatively, that's it. So that's the end of this particular sub-lecture. We learned how to do some calculations with the second law of thermodynamics.